Hey guys, today's lesson is on quantum numbers. So, what are quantum numbers and what do quantum numbers do? Well, quantum numbers help us determine the electron configuration of an atom and the probable location of the atom's electrons. So, there's I don't know really the best way to think about it because it's all up to you. However, personally, I like to think of quantum numbers as in parts, okay, and like a checklist, okay, because there will be a lot of questions on exams or homeworks that ask you if this is a possible configuration, and you have to go back and see if every single thing is right and is checked off. So, let me just write down some things. Quantum numbers. So, we have the principal quantum. Oh geez, I'm spelling that wrong, ignore that. Number. And that's just basically the energy level. And that's going to determine the size. Okay? Then we have the angular momentum quantum number. And that's going to determine, let me write down also, this is going to be N, and this is going to be the cursive L. That's going to determine, or that is determined, that determines the shape, and there's only so many possible angular momentum quantum numbers because it's just going to be N minus 1. It's going to go up to N minus 1. Okay? So it could be like 0, 1, 2, and 3 if N equals 4. But if N equals 2, then it's only going to be 0, 1, 0 and 1. Sorry. And let me get some more. Let me see if I can move this a little bit. So we have those two. Then we have the magnetic quantum number. Okay, and that's going to be M and then subscript cursive L. And that's just going to be equal to 2L plus 1. So if L equals 3, okay, and I'll get to this in a second, that's going to be in the F subshell. But if L equals 3, then you just plug it in and you get how many possible ML values there are. Okay, so if L equals 1, then you're just going to plug that in and you're going to get 3. Okay? So the last one is, that's going to be the magnetic spin. Magnetic spin. Okay, and that's going to just be M subscript S. And there's only two possible values for magnetic spin. There is positive 1/2 and there's negative 1/2. Okay? That's just because there can only be two different electrons, so the positive and the negative. There can only be two different spins within a shell. So, alright, that is, oh, and let me go over here. I created this beautiful periodic table. So, this is the first, so for the S, this is S, oh jeez, the S shell, okay, this blue, this is the P, this is the D, and this is F. Let me write that. okay? And the s subshell is always going to, the L is always going to equal 0. For P, the L is always going to equal 1. For D, L is always going to equal 2. And for F, it's always going to equal 3. Okay, I'm just going to sum up what I previously just stated. For the s orbital, let me write a better s. For the s orbital, because L equals 0, there can only be, ML can only be 0. Okay, there can only be one value for ML. And for the p orbital, because L equals 1, oh geez, because L equals 1, ML can equal -1, 0, and 1. So it has 3 values. I'm going to write 3. Okay, and then for the d orbital, same thing. However, L equals 2, and ML equals -2, -1, 0, 1, 2. And it has 5 values. With the f orbital, again, same thing. L equals 3 now, but ML, and I gotta get more space for this, equals -3, -2, -1, 0, 1, 2, 3. So it has 7 values. So instead of wasting your guys' time trying to draw these images, I just decided to pull them up. And I mean, as you can see, the number of magnetic quantum numbers correlates with the number of different possible shapes, right? Or orientations, better, because these are all the same shape, they're just oriented differently. But here are all of them. So S has 1, like I said, P has 3, D has 5, and F has 7. Okay? And I mean, you can't just go right to the magnetic you can't just go right to the magnetic quantum number. You have to know the principal quantum number. So let's say it's 3. Then you can determine what L's go with that. So it could be 0, 1, 2. And then based off that, you can figure out, okay, so there's let's say it's 2L, okay? So that's -2, -1, 0, 1, 2. Okay, 5. So that's, boom, D. So it's going to be in the D subshell. So it's probably going to be a metal. And it's going to be on n equals 3, so it's going to be the first row. Okay? It's pretty simple. You just have to take your time and go back and see if things, see if things make sense. Because if I've got n equals 3 and I have L equals 4, no. If I have n equals 2, L equals 1, and m subscript L 3, or -3, no, that won't work. So you just have to make sure, you have to check off those boxes and make sure that yes, that's right. Okay, wait, that might be too much or too little of what it actually should be, or it's not in the correct range. So just make sure that everything flows together and makes sense. Alright, radial distribution. This was something I actually enjoyed learning. I enjoyed it a lot, obviously, because I'm making these videos. Oop. However, this was something that I really did like. Okay, there we go. That's kind of sucked, but whatever. So, what is radial distribution? Radial distribution is the overall probability of finding an electron the farther out you get from the nucleus. So basically, as distance increases, how likely are you to find an electron where you're looking at? So let's start with this color, a little blue. So if you're looking at the 1s orbital, you are very likely to find an electron in the 1s orbital. if you're, let's get a new color, looking at the 2s orbital, you are actually still likely to find an electron in the 1s orbital. It's just not as likely. You're not gonna. So basically, this just shows that. And let me put a little boom. And I don't even remember what color. I think this. You're not. It's not 100% you're gonna find an electron right here. Okay. If you're looking at the 1s orbital, you're not. It's not 100%. Okay, because the electron could be over here closer to the nucleus or over here farther away. Okay, it's not going to be perfectly right there where the 1s is. I don't know the exact distance, but wherever that is, it's not going to be exactly right there. Same with the 2s. Okay, they're not all going to be right here. There's still going to be somewhat of a large probability of electrons still being found in the 1s that are actually 2s valence electrons. Okay. And let me get the third one out here. So for 3s, still likely, and then boom. Let me write 3s. Okay, and an important thing to note: this is a nucleus. This is 0 away from the nucleus. Okay, you have a 0% probability of finding an electron at the nucleus. Okay. And you also have a 0% probability of finding it at the nodes. Okay, there are no electrons at the nodes between the whatever, right? You have a 0% possibility of finding them. And that is pretty much all there is to it. I'm trying to think. I don't think there's anything I'm really missing with this. It's pretty straightforward. Okay, basically, the farther out you get, the less likely you'll find the 1s. However, there still is a possibility, and it's never, technically, it's never 0. It goes on forever. However, if it gets past a certain point, it virtually is not even a part of the electron cloud. So, just keep that in mind as well. Like, if it's all the way out here, you're not going to find it. Or it's not going to technically be a part of the molecule's electron cloud. Alright, time to do a problem. So, what are the n in cursive L, just L, quantum numbers for the outermost electrons in S2- ion, or in the S2s ion? So we're looking for the principal quantum number. Principal. I'm just going to do Q number. Okay. We don't know what that is. And we're looking for, I don't even want to write this one down, the angular momentum quantum number. So just L. We don't know. I'm honestly going to get rid of that. So we're looking for N and L. Oh my Lord, have mercy. N and L. So we know, honestly, in another tab, pull up a picture of a periodic table, and when you pull it up, you'll be able to see that for sulfur, it is in the 3rd energy level, okay? And the energy level is basically just a principal quantum number, so N is going to equal 3, okay? And we know that the angular momentum quantum number, because it's in the p subshell, is going to be 1, okay? So, I mean, it's really that simple, and we could go on and on and on, and we could figure out the electron configuration, which honestly, let's just do that right now because that was too easy. So, the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, and I'm just going to do for generic basic sulfur, so it's going to be 3p4, okay? However, when you make that an ion, or anion I guess in this case, but an ion, it's going to end with 3p6 because you're adding 2 electrons, and this is going to make it more stable. Okay, it's not going to want to react with other elements because of how stable it is. Okay, it's already at like it already has a full shell, so it doesn't want to. It's not highly reactive, and yeah, that's pretty much all there is to that. Okay, here's the second problem I have for us. How many values of m subscript L, so the magnetic quantum number, are allowed for an electron in a 4f subshell? Okay. So let's think about this. It's in the 4f subshell, so I'm going to do a little rough sketch of the periodic table. It's good enough. Forgot that little part. So let me. You know what? Ignore that. So it's in the 4f. So here's the periodic table. And there's F. Okay, so here's S. Here's P. There's D. And there's F. And what is the angular momentum quantum number? What is L of F? I'm going to give you guys a second. Answer it. 3, 2, 1. Should know it off the top of your head. It's 3. Okay? Because 0, 1, 2, 3. Alright, so we have the angular momentum quantum number. Now everything is super easy. So, I mean, you get, we're looking for how many values, so we don't even have to say what kind of values. You just have to know the little equation I gave you, which is 2L plus 1. Okay, so 2 times 3 plus 1 gives us, boom, 7. Okay, final answer, locking it in. Super simple, super easy. Again, that one was too easy, so here's another one. You guys do this on your own. What about, how about a 3p? What would how many values would there be for ml in the 3p subshell? I'll give you guys a second. 3, 2, 1. Okay, we know it's in the p subshell, so it has to have L equals 1. And when L equals 1, we just plug that into our equation, and we get 3. Guys, it's really that simple. Don't overcomplicate things. Take your tests slow, but don't take them too slow. Okay? This is something that should, if this was asked on a test, this should take you 10 seconds. And I'm not even kidding with that. This is a 10-second question. Because you read it, how many values of ml are allowed in an electron in a 4f subshell? Right when I see the F, 4 doesn't even matter. Right when I see F, I automatically know L equals 3, ML equals 7. Okay, and boom, you circle 7 for D. Boom. Good luck, guys.